Okay, in our previous class, we learned about the ordinary Hall effect, and I mentioned that there are so many kinds of Hall effect, and the ordinary Hall effect can be occurred in any kind of conductor, but so it is very important, but we are working on the ferromagnetic materials. So usually in the ferromagnetic materials, the anomalous Hall effect is more important. So in a ferromagnetic material, we have a magnetic moment inside of our samples without any external magnetic field. For example, if we have an electron inside of the ferromagnetic conductor, then they feel some kind of internal field because of the magnetic moment. So the Hall effect is originated from the ordinary Hall effect, and we have additional one. The ordinary Hall effect proportional to the external magnetic field, and the other one is proportional to the magnetic moment of the ferromagnetic material. And generally, the external magnetic field order of kHz, and the magnetic moment is order of 10 kHz. Or in other words, this is order of 0.1 Tesla, but this is order of Tesla. In addition, the coefficient of the coefficient of the anomalous Hall effect, called RS, is generally larger than ordinary one. So generally, the measure of the Hall resistance is proportional to the magnetic moment. So for example, in this measurement, we measure the typical ferromagnetic samples, and the Hall measurement represents such kind of loops. Yes, this actually looks like MH loops. So the ordinary Hall effect is very useful to measure the MH loops, even though the y-axis is not the M, but they are proportional to the M. So we can measure it for very thin film, where if the film is very thin, typical measurement of the magnetic moment is not easy because the total magnetization is not so large. But this transport measurement or Hall measurement gave us the shape of the MH loops. So in this measurement, we can obtain the coercivity very easily. And you can see the shape of loop is quite like the Wahlfarth model result. So it's behave like a single domain. So in ferromagnetic materials, such anomalous Hall effect is much more dominant. But we have another example here. Let's think about the nickel aluminum alloy. Here, with the alloy of the this nickel aluminum, those materials are paramagnetic, so they have a anomalous Hall effect. Ordinary Hall effect, which one is proportional to the external field H. So they are linear to the field. But in this case, they are magnetic. So there is some two contribution. One is linear one to the field, and this part is because of the anomalous Hall effect. So generally, this contribution is much larger. And here, see, the external field is somewhat larger in this case. So this law looks like measurable, but if we play with the small field, there is no such contribution or very small contribution. And other thing is, this is very weak ferromagnet. That's why they have such kind of a small contribution of the anomalous Hall effect. But in generally, in strong ferromagnet, the contribution of the ordinary, the anomalous Hall effect is much larger. Then what is the possible origin of the such anomalous story path? When we measure the anomalous story path, we have two contribution. In this anomalous story path proportional to the linearly to the perpendicular resistivity and the square of the perpendicular resistivity. So those coefficients A and B give us different origin. There are very famous two possible origin. One is called the skew scattering, and the other one is called the side jump. As you see here, the skew scattering means if we have an electron, conduction electrons, and there is some impurity, the scattering loss, and in that case, the scattering angle is not symmetric. Without any symmetry breaking, the scattering angle must be symmetry, something like this. But because of this magnetic impurity, they preferred such kind of scattering directions. So the overall scattering occurred to the they are breaking the symmetry. So we have more electrons to these directions. That's called the skew scattering. And the other one is called side jump. This is purely quantum mechanical one. For example, if we have a conduction electron in this direction, and if we have some kind of angular momentum exchange with the scattering center, then this conduction electron has a finite angular momentum. That means there is some shift of the scattering directions, so they have a finite contribution to the one directions. So that's also the cause of the anomalous story path. And this side jump concept is not easy to understand in a classical point of view. But just to think about that, if you have a charged particle here and another charged particle here, there is some kind of a distance between them. Then they have some kind of scattering. This is called, we call impact parameter. Yeah, you can easily find that terminology in a scattering theory. So in this case, this impact parameter play with the angular momentum because we have a mv here, and this is finite distance d. Then they have such angular momentum. So this side jump is something like this. So this side jump and skew scattering is origin of this anomalous story path, but they are also played very important role in anomalous MR, which one we are gonna learn, and spinori path and inverse spinori path, which one is very emerging field in spintronics. So those two mechanisms is very important to understand the transport property in spintronics. Okay, and so far we are talking about the Hori path, and now we move on to magnetoresistance. Please keep in mind, in a Hori path, when we have such kind of current, we measure the voltage change in a transverse direction. But in a MR, we measured the longitudinal transport. Okay. So let's think about this case. If we have an electron here, there is some scattering. So this is called the mean free path of the electron when H field is 0. What happens in a non-zero H field? The trajectory of the electron itself is bended. and this length must be same to the mean-free path with zero field. But this direction, which one is the longitudinal to the current direction, is getting shorter. And this lambda h can be obtained by this simple rule. Here the r is this direction, this distance, and theta is here. Theta is here. So if we have a theta is defined by lambda 0 over r here, in the first order, lambda 0 because of sine theta in theta minus such form. So we have a this relation. So this amount is decreasement of the mean-free path, and the conductivity of the metal is proportional to the mean-free path. So we have a decreasement of the conductivity. Okay, and here we can see the r and this r is a cube will be cancelled out. So the delta of the mean-free path is proportional to the r, 1 over the r square. And this r is nothing else but the radius of the circular motion of the electron in our external magnetic field. So yeah, if we have a electron in a magnetic field, then the Lorentz force is in this direction. So they are acting as a centrifugal force in this relation. So we have this relation R is QB MV. So this radius means there is some kind of circular motion of electron inside of the B field, and this radius is same to here. So this means they are proportional to B square. So we obtained this relation. So that implies that doesn't care about the direction of the field. They are scale of the field. So they should be even function of the external magnetic field. And in this case, we have a negative resistance. That means the resistance can be decreased with the external magnetic field. And we define the whole resistance by, we already defined the whole resistance, which one is proportional to the H. So there are some difference. This is H square, this is H. So, this ordinary MR, we can observe in any kind of conductor. Yeah, this explanation is very simple, but the truth is there is something more. Yeah, this simple explanation is not quite correct, because as we already learned in a Hall effect, actually the effect of the external magnetic field will be cancelled out because of the internal charge of the let's say without external magnetic field, the trajectory of the conduction electron is just straightforward. But with the Hall effect, with the external magnetic field, there is some bending. So we have an extra charge here. So there is some kind of internal field is developed, and this internal field is cancelled out the effect of the magnetic field. So we have such relation. That's the condition of the finding the Hall effect. So when they satisfy this condition, there's no more bending. So we are still keep this term. So there is some dilemma. If we think about this effect, there is no ordinary MR. But the truth is, this model we assume just a very simple conduction electron like a free electron. But in many solid states, the band structure is not that simple. So when we think about the different band model, like a multi-band, we can recover this relation again, but they require more complex mathematics and more physics. So just keep in mind, this simple model can explain the ordinary MR, but it's not quite correct. It's too much simple. That's the one point you have to remember. Okay. And yeah, we already mentioned the ordinary MR. That means we have another MR called AMR. AMR is also very important in ferromagnetic materials. And this A stands for anisotropic MR or anomalous MR. Sometimes we call this is anomalous one. Yeah, those two means actually there is some same meaning. So in AMR, we have a square term of the field and the square term of the M. Square term of the M. And as we already mentioned in anomalous Hall effect, those contribution is smaller than this one. So usually we think about this term. So this first term came from the ordinary MR. The second term is originally came from the scattering because of the magnetic moment of the inside of the samples. So when we measure the MR with the external magnetic field, the general behavior is something like this. Yeah, when we measure the MR, there are two geometry. One is if we have a sample here and conduction, the current is passing through this direction, and measure the voltage here. And if we apply the magnetic field to this direction, this we call the parallel one. And if we apply magnetic field to this direction, we have a perpendicular one. So when they saturate the field is strong enough, then all magnetic align to the current direction. We have some certain value. But when we decrease magnetic field, then let's say we have such kind of image loops. Yeah. Then there are some kind of a domain occurred, which one the domain's magnetic direction is not parallel to the external magnetic field. Then they behave like a scattering source, so the resistance increase. And then they are starting to align to the opposite direction, so their resistance decrease again. And after they saturate, if we increase the field again, we have such behavior. So one important thing is this peak point is corresponding to the Cauchy field in image loops. And in a transverse, one is this direction, then the parallel one or longitudinal one has a MR but a different sign. So when we measured the transverse one and the longitudinal one, they always has a different sign. Yeah, sometimes in some material, the transverse one has this sign, this negative MR, and the parallel one is the positive MR. But it depends on the materials. But they should have a different sign. Okay. And this, in this case, with the field, large field, this is the very small field. This is the order Wester, this is Q Wester. So this linear behavior represent, actually this is not the linear, this is the H square term, is -1. This is from the ordinary MR. But this contribution came from the anomalous rod. But in generally, yeah, this is the kind of a weak ferromagnet, but this is a strong ferromagnet. So we have a such shape. So the measured AMR is also another technique to characterize the magnetic property of your samples. And also the origin of the AMR is quite similar to the anomalous Hall effect. Yeah, there are very similar physics in anomalous Hall effect. Yeah, there is some explanation. If we have some kind of infinity here and positive charge in infinity, and you have an electron, and when electron is passing through here, because of the Coulomb force between them, we have some bending. Okay, that's the general scattering. But we have an extra one called the spin-orbit coupling. So when the electron is in this direction, we have a spin moment here, and we have a finite angular momentum in this direction. Because this is the linear momentum and this is the distance, so we have such angular momentum. So if we have a spin and the angular momentum, we have a finite spin-orbit coupling. So when if we don't have any spins, then there is some kind of a Coulomb scattering. They should be symmetric. But because of the spin-orbit coupling, there is some kind of additional contribution. So we have a asymmetric or anisotropic scattering. Okay. And also, to understand this AMR, we have to understand the true quantum model, which implies the conductivity of each spin, means the majority and minority spin has a different conductivity. I'm going to explain it like the slide. Okay, before explain the true quantum model, we have to briefly remind the Drude model. Here I have one question to the student. Do you guys are familiar with the Drude model? Anyone who never heard about the Drude model? Yeah. Is there anyone never who don't know about the Drude model? Okay. Then I'm gonna explain very briefly. In the Drude model, we assume the conductor, we have a positive charge, which one is fixed position. Then they are not moving, and the electron is moving between this positive charge, but there is some finite scattering with this positive charge. And if we have a plus charge here and electron, and after they collide, after collision, the electron can be scattered any direction. It's random. This scattered electron lost the information of the before scattering. And also we assume the mean collision time tau. Yeah, call this tau is mean collision time or the relaxation time. And there are many names. But the important thing is we assume such kind of average behavior. Yeah. So after a collision event, the velocity means the here means the magnitude and the direction. They are random. So let's think about that. The external field, because of the external electric field, that means if we have a some conductor here, if we apply the voltage between them, we have a internal internal E field, and each charged particle feels some force, the Coulomb force, like QE, and QE is accelerate the electron to the field direction. And now we think about the thermal motion of electrons. So actually, without external electric field, the motion of electron is quite random, and they are freely moving and very fast. But the average value of the velocity must be zero, because without E field, there is no net current to any direction. But with this E field, we think about the average value of average velocity of the electron and or average momentum. And this momentum must be QE tau. Yeah, because the delta P over tau means the change of momentum during this collision time should be QE. So we have such relation. And with this relation, think about the current density. Current density is current divided by the cross-section area here, and this current is number of charged particle and relaxation time tau again. And here we can introduce the area. Yeah, this is the cross-section area here, and the volume. We are talking about this volume. V is A over L. And this L means the mean free path, which one is corresponding to the distance between each collision. So this L mean free path should be 3 tau. Okay. So with this relation, we replace this A by volume and the mean free path here. And the small n is defined by charge carrier density, so the number of charge divided by volume. And we have such relation with L mean free path divided by tau. So we have this relation. So the charge current density J is, can simply write this form. And then the V we can obtain here. V is QE tau over M, right? So we can rewrite here NQ square tau over M and E field. And this term is the conductivity. And in this simple Drude model, we can obtain the conductivity of the metals in this form. Here we replace M by the M star, which one is the effective field, effective mass of the electron and a given band. And tau is the scattering time. And this is the charge carrier density, and we have a scale of the charge. Okay. Yeah. In this derivation, we assumed such kind of friction force is proportional to the velocity v. If we rewrite the force acting on an electron, Q is the force because of the electric field. And we can write down the friction force instead of the collision concept. We can rewrite this form, which is proportional to the velocity of the electron. And when the E field is the external force is zero, means they are balanced and no more acceleration. That implies the terminal velocity should satisfy this relation. Actually, they are same result in a previous case. So from this relation, we can obtain this one again and the Drude model's result. So here, the funny thing is actually this is called the microscopic Ohm's law, and from here we can obtain the macroscopic Ohm's law again. So this Ohm's law is well validated by the experimentally. So that implies the friction force is proportional to the velocity. Then why this should be just linear to the velocity instead of some kind of power, let's say V alpha? The truth is, actually, there is some kind of linear term and square term and maybe cube term. It can be exist. But in many cases, those terms are not important and they are negligible. Only the linear term is leading term. So such kind of linear friction model is quite valid in many solid state materials, but sometimes they are not true. You can find some kind of nonlinear behavior or breakdown of the Ohm's law. For example, the semiconductor and many other materials. But in a metallic system, such linear behavior or linear friction model is quite a good one. Okay, so let's think about the density of state of the 3D metals. Actually, I already mentioned this graph previous in maybe a few weeks ago. Yeah, we already learned this conductivity. And here, this conductivity implies the conductivity of electron for each band can be different. And if we think about this M star and the tau, yeah, let's recall this simple model. In a alkali metal, we have only S electron. And this is the density of state because of the S character, S band have such kind of parabola shape. And the conduction electron is important at the Fermi level. So generally, this alkali metal has a very good conductivity, means the small resistance. This is the resistance. Resistivity, sorry. This is the inverse of the conductivity. So they are small means the conductivity is large. But in a noble metal, copper or silver, we have a D band, but they are below the Fermi level. So there is no contribution of D band. So only the S band contribute to the conduction. So also they have a small resistivity. But in a non-ferromagnetic material, but in 3D transition metals, there is some D band, and the density of state is quite large. And this scattering time, the inverse of the scattering time is proportional to the density of state. What's that mean? If there is many electrons, if we have a large one, then we have a small scattering time, means the scattering occurred more frequently. So you can easily imagine in this D band as a large n of state, and then implies small tau, then the conductivity is getting smaller, or the resistivity getting larger. And the other one is also the effective mass of the band. Generally, the effective mass of the band, of the D band and S band, the effective mass of the D band is getting larger, because the effective mass, we think about this simple electron model. Yeah, this equation implies such kind of parabolic shape of band. And it depends on this effective mass, the band shape can be changed here. The small effective mass M, we have such kind of band. Which one is called S band? And if we have such kind of heavy band, we have this is a kind of D band. So in a 3D transition metal, we have a small tau and large M. So generally, the conductivity is getting smaller. That's the general behavior of the conductivity of the 3D metals, the metals. And let's think about the ferromagnetic materials. Here, we have two kinds of band for the spin down and the spin up. And the Fermi level of the spin up is different from the spin down case. And also, even though the effective mass can be same, but this tau for spin up and spin down cannot be same. So that means the conductivity of the spin up and spin down cannot be same. Yeah, this is very important concept in a ferromagnetic materials. Okay. So let me introduce about the two current model. Generally, in a spin is another called is angular momentum. So in a Drude model, we think about many collisions of electrons. Each collision, they lost their linear momentum. After collision, we have another angular momentum. They are not same. We have a linear momentum, and this linear momentum is not conserved for each collision. Then the linear, by the momentum conservation law, the loss, we have to transfer this linear momentum to this positive ion. So after collision, the positive ion get some linear momentum or kinetic energy. So that's what the cause of the Joule heating. But if we think about this angular momentum, because this ion has no angular momentum, so after collision, each spin their angular momentum because we cannot transfer the angular momentum to the ion. So with many collisions, they are still keeping the direction of the magnetic moment, the spin direction. So that's why we call the two spin current, two current. We have actually single materials, but inside of this material, we have such kind of two resistance for the spin up and spin down with a parallel connection. After such collision, finally they are losing their spin information. That's called the spin diffusion length. So within this spin diffusion length, we can consider the such kind of model. And within this length scale, each spin current behave independently, so we can make such form. But what happens if we exceed this spin diffusion length? Then there is some path between these two. Let's say there is some kind of a current path between them. So spin up electron can be spin down or the other way. That's called the spin flip. So if we consider this part again, it's getting complex, but within the spin diffusion length, we can easily using this simple model called the spin two spin current. Okay, so in this two current model, we can easily explain about the GMR. Future is another MR, and we with the name of the giant. In AMR is order of 1 or 2%. Means the resistance changes is around 1%. But 1% is not that large, but still it is good enough to using some kind of sensors or some devices. But if we get MR is getting larger, it's better. So the GMR means there's some kind of MR with a very large amount. So simply, let's think about this simple layer structure. If we have a cobalt, two cobalt layer, and they are sandwiched by the copper. Copper is a typical non-magnetic material, but the conduction is very nice. So when we think about the parallel configuration, the magnetization direction of these the two ferrite layer are parallel. Then, if we have a low resistance for the spin down case and high resistance for the spin up case, then spin up electron here is there is some many scattering inside of this cobalt. And also in this second cobalt, there is some more scattering here. So we assume the resistance of the this spin up is large. And spin down case, there's no strong scattering, so the resistance of the spin down is small. The same in here. So without any spin flips or spin scattering, we can make such kind of resistance model. This is a cobalt layer, this is another cobalt layer, and there's no contribution of copper between them. This is copper. We assume there's no resistance in the copper. Then the spin down electron can pass through this way, and spin up is passed through this way. And now let's think about the anti-parallel case. The magnetic moment, magnetization direction of second ferrite layer is not the same. They are anti-parallel. Then the spin down electron has a low resistance here, but they have a large resistance in this state because this spin down is relatively spin up in this direction. And same thing happens for the spin up case. There is a large resistance, but here small resistance. So this model is changed to this shape. So in this case, there is a small resistance path, so there's more current here. But in this case, there is some kind of large resistance in both sides. So you can simply calculate by circuit model. This parallel case and this anti-parallel case, the resistance of the anti-parallel case is getting larger, called high resistance state and low resistance state. And the ratio of the difference of the is order of 10%. Yeah, 10% is since not that large, but it's order of 1 magnitude is larger than the AMR. So that's why we put the name of the GMR. Yes, 10% MR. With this 10% MR, we can use this MR effect in many applications. So in extreme case, if we think about the very extreme case, in the parallel case, this pin can be passed through, while this pin cannot pass through because and in an anti-parallel case, we have a pass through here, but they are blocked here, and the electron is blocked here. So in this case, we have a finite current, but this is zero current. So in this case, this is conduction, this is insulator. It's two extreme case, but the real sample has not such kind of 100% MR, but we have a large MR. You can understand the observed GMR by this simple model. Because of this discovery of the giant MR or GMR, two guys got a Nobel Prize at about 13 years ago. Okay. And this GMR played a very important role in boom of the nanotechnology. End of the last century or beginning of this century, many people very excited about the nanotechnology, and there are many very promising predictions about the nanotechnology, but many of them are not realized at all. But GMR is one of the good example of nanotechnology, which will help a lot in the industry. With this GMR head, we can make a much better hard disk drive, and we can increase the capacity of the hard disk drive a lot. And such a large large amount of hard disk drive can be boost up the development of the internet. Yeah, just imagine that if you have a fast internet connection, and if your hard disk drive is very small, let's say just 1 giga, then what can you do? Because you have a very large hard disk drive, you can download some music and video clips or some movies very easily. So such contribution is very important in industry, especially in IT. So that's why they got a Nobel Prize. And here, one more thing. How they can discover this GMR? Yeah, such kind of layer structure is very simple, but why nobody can find such a simple phenomena? The reason is the thickness of kappa must be less than the spin diffusion length. So they should be order of nanometer. The layered structure, in a layered structure, control of the nanometer thickness is actually not that easy technology. Nowadays, it's not so difficult, but at the 80s or 70s, such control is very high technology. So if you make some kind of new fabrication technology, you can find, you have a lot of chance to find a new phenomena. And another thing is how we can control the direction is parallel and anti-parallel. If we apply the external magnetic field and if this quality are identical, they should behave the same. So they can be only parallel, and if you apply the external magnetic field in a opposite direction, you can switching together. So this GMR was found in some special structure. There is some kind of strong coupling between two layers. We already explained about the interface exchange coupling. Yeah, because of the interface exchange coupling, the ferromagnetic, if we have a two ferromagnetic layer sandwiched by the non-magnetic material, there is some coupling. And depends on the materials and the thickness, sometimes they prefer anti-parallel configuration, or sometimes they prefer the parallel configuration. So if we set the anti-parallel configuration, we can obtain this configuration. But if you apply strong magnetic field, they are prefer the parallel configuration, you can obtain this one. Yeah, actually, after people finding this inter-exchange coupling, the GMR can be easily found. Okay, so every discovery are connected to each other. Okay, and in hard disk drive, we have a lead head, which one is lead the stray field from the surface of the hard disk drive. And if we have a sensitive sensors, we can make a smaller bit. Means we can increase the density of the recording information. So the better magnetic field sensor means you can make a better hard disk drive, or you can increase the capacity of the hard disk drive. Okay. Actually, we have some schedule today, so I should stop today's lecture here. But maybe I can get just a simple one or two questions. Do you have any questions? Oh, questions. Yeah. If we working in a room temperature, the typical Curie temperature of the ferromagnetic material is order of 1,000 Kelvin. So in this room temperature is smaller than the TC, then the all magnetization direction is almost parallel. But in a TC, there is so many misaligned spin because of the thermal motion. So that means there is many spin can be generated. So in this case, with a small perturbation, extra spin can be easily excited. Then that means spin excitation means the conduction electron lose their angular momentum. So this two model is no longer valid, around the TC. So, well below the TC, much lower than the TC, then the two current model is valid. Is it okay? Okay. Then let me close this class here and oh. Oh, in LMS system, you can easily find the recorded one. Yeah, if you cannot find it, please let me know. Then I will let you know more details. Yeah, in a GMR, there are two types. One is the multi-layer case, like this. The GMR call is something like this. In a parallel case, the low resistance. In an anti-parallel case, large resistance. But in a special design called the spin valve, then they have such kind of a shape. It's different. Yeah, I'm sorry, I don't have time now, so I'm gonna explain it maybe next class. Okay. And if any student about who knows about the recorded file, then let Taeyong knows. Okay. Please Taeyong ask to your student, your friends. Okay, then see you next Monday. Okay, bye.